I've got like 10 minutes, everyone. When someone is weightless, do they mean that they are in the middle of outer space and they have no weight? No. If you're falling, you're weightless. Because what causes you to feel weight? What do you actually feel? Remember, we talked about this at length twice. We talked about it about 2 or 3 weeks ago, and we also talked about it on the very first day. When you're on a floor. Yes?
Oh, did you want me to answer? Are you about to go into the explanation, or do you want me to answer?
No, you can answer that. It wasn't a rhetorical question. You can answer that on it.
Attraction between your body and the earth, and it's your body pushing against the earth, and the earth pushing back up against your body, and that's what you feel.
Yeah, that's correct. That's correct.
Is there any way in like space to make yourself feel weight? Like a vacuum thing or whatever?
Rotation, right?
Yeah. Yeah, if you have a rotational spaceship, you can certainly create centripetal force and you would feel weight.
But is there like a way that you can just like be in your like spaceship and just be walking around?
I remember years ago there was a movie called 2001: A Space Odyssey. Have you ever seen it?
No.
Well, in that movie, if I recall correctly, wasn't there a space station? And in that space station, it was circular.
Yeah, and it was rotating around.
And it was rotating around, and they could walk on it, if you think about it. If you spin something around, right? A centrifuge, okay? There's no such thing as centripetal force. But if you have a centrifuge, like this, going around and around and around, you have a relationship here. There are forces counteracting, okay? So that would make this, if you're here, you would feel what you would consider your weight, and you would also feel your, the upward weight, the upward force, which would be the normal. So you could manufacture the feeling of that you have weight. That's not on Earth, and it's the same exact idea. For instance, when you're on Earth, you have your weight, and what you feel is the normal force, because you're supported, okay? Equal and opposite reaction, correct? Newton's third law. If I take away the normal force and I fall, don't I still have weight? Of course I have weight. I'm accelerating, correct? However, the apparent weight is going to be zero, right? It's going to be I'm not going to have any weight, but my weight is still going to be there. I'm still going to have weight. But I don't have the normal force, there's no counteraction to that weight. So if you fall or are in free fall, like for instance if you're in an elevator, let's say this is an elevator and the elevator goes down, and you know as well as I do that when the elevator goes down, what can it continue to do? If you're going down, has anybody ever been up to the top of the Burj Khalifa? Yeah. Have you? When you descend, I have never done it. What's it like? Is it your ears go? Yeah? Do you feel light? Do you feel like, whoa? Your stomach kind of goes up into your ears, between your ears. So your stomach goes from here up to between your ears, and then what does it do? It goes back down to your stomach, right? So what can't the elevator do in the Burj Khalifa when it's descending back to the ground? It can't do what?
Provide a force against.
It can't continue to do what? Anybody? It can't. May I help you out a minute? Okay, it can't continue to go faster. It can't continue to accelerate. Yes? You have this moment where you have this acceleration, don't you? And then it stops accelerating and it reaches a constant velocity, correct? And that constant velocity, then you have no more acceleration, so your weight is your weight. So when you're going down in the elevator, you have this momentary acceleration where you have ma and you're creating this downward force, but this opposite, so you're subtracting that, aren't you, from your weight. So you have this momentary subtraction from your weight, don't you? Correct? Yes? If it accelerates in terms of 1g, what's your weight going to feel like if it accelerates downward 1g? It's going to be, your apparent weight will be 0, correct? Because this is what your weight is. This is 1g, that's your weight. I'm standing right here, it's 1g. If I accelerate downward 1g, then I'm not going to have any weight. I'm not going to feel that I have any weight, correct? My apparent weight, correct? You're going to subtract from it. Yes or no?
Yes.
Okay, so if I do, you know what I'll do? We'll do an experiment where we set this up. I'll explain, but we'll do an experiment. It's called the Atwood machine. I actually have an experiment on in the folders for physics. We'll do an experiment, and you'll see how this is true. Okay, it's not going to be a physics class, Mr. L's physics class experiment. It's just going to do an experiment, and it's going to be, we'll keep it simple, okay? But it can't continue to do that. It has to come back down to a regular velocity where now all of a sudden your weight's your weight. Yes, Brianda?
What are the two forces? One is gravity, correct? And what's the other one?
The floor pushing up. I push against the floor. The floor pushes against me. If I'm in an elevator, the floor is the floor of the elevator. I'm pushing down on the floor of the elevator. The floor of the elevator is pushing up against me.
But gravity is the thing that's like pulling us down.
Correct.
But what's the thing that pushes against us?
The floor.
The floor literally pushes
Correct.
against us.
Absolutely. As much as we push against the floor. See, that's one of the difficulties in teaching an astronomy course this way, because half of my class has had physics and half has not. But if I push against this, correct, with 100 units, 100 pounds, you're American, right? So if I say 100 pounds of pressure, that makes sense to you. 100 pounds, I push against it, the wall's going to push back 100 pounds. How do you know it pushes back only 100 pounds? How do you know? How do you know? How do you know? Because it's not accelerating that way. If there was a difference, in other words, if I push against this 100 pounds and the board only pushed back 90 pounds, what would happen? I would accelerate through the wall, right? If I push 100 pounds and the board pushed back 110 pounds, what would I do? I would accelerate that way. So I know, because I'm not moving, that if I push against this with 100 pounds, it's going to push back 100 pounds. If you go to the carriage in the store, where I can push that full cart with essentially a finger, because I am only pushing that cart relative to the amount of friction I need to overcome. Once I get that cart going, once I overcome inertia, I'm going 1 mile an hour. Once I get that cart going down the aisle, okay, then I simply have to only apply enough force to keep that car going, because it's going at a constant velocity. So I'm only applying the force that overcomes friction. If I apply a force that's greater than friction, my cart will accelerate.
So if you're on the moon, because the moon doesn't push back as much, that's why...
I don't weigh as much.
Because we still have gravity on there. And
Correct. So if I'm, correct.
Gravity.
If I'm not moving, I'm pushing against the moon is pushing against me. The moon is smaller. Therefore, it's not going to push back as much because I'm not going to push as much. So the force that way still equals that way, but it's less. It's still zero. The difference is still zero because I'm not accelerating downward towards the center of the moon. Correct? What we'll do on Thursday, because we did the homework today and that took some time, on Thursday we'll finish. Okay? We'll talk about tides, black holes, and finish up some sketchiness with gravity, etc. Okay? Have a great homework.